Let's investigate the maximum and minimum values of a function. These are always worth investigating because in some ways they indicate turning points of a function, and it's a turning point of a model. And there's different kinds of turning points, but certainly locating maximum and minimum values is certainly one of them. Here's a couple of warm-up problems that you can do to help you improve your study of calculus. But our objectives today is to learn definitions of absolute max, absolute min, local max, and local minimum, all relating to a function. We want to be able to find critical numbers. This will allow us to take careful analysis of differentiable functions. And then we'll look at a special case where we could actually find the absolute max and absolute min of a differentiable function in a closed interval. So there is a difference between closed intervals and open intervals that you learn from algebra. We'll begin with a definition. We want to think about absolute maximums of a function. Let function f be defined on a domain of f containing an x value called c. If f of c is greater than or equal to f of x for all x in the domain of f, then f of c is the absolute maximum on the domain of f. Think of the domain of f as the world in which the function lives in. Okay, it is the universe. It is the world. Similarly, if f of d is less than or equal to f of x for all x in the domain of f, then f of d is the absolute minimum on the domain of f. Once again, you could think of the domain that you learned from algebra to be the universe or to be the world for that function. So what's the difference between local versus absolute? Okay, you want to think of local as, as a neighborhood, and absolute could be the city. All right, so which one is smaller? The city or the neighborhood of a city? So local means it kind of sounds like, your local trip to the local grocery store. It shouldn't be that far away. So here's another definition. Suppose f is defined on an open interval I, and that will localize or pinpoint a smaller location. And c is in this open interval. If f of c is greater than or equal to f of x for every x in I, then f of c is the local maximum value of the function. Similarly, if f of d is less than or equal to f of x for every x in this open interval I, then f of d is called the local minimum value of this function. So here, when we talk about locally, we just observe an open interval near c and an open interval near d. Why don't we do that with a graphical example? So here is a function. And the output values are right there. Sometimes it increases, sometimes it decreases, then it increases, then it decreases again. Now what we want to do is look at this locally. So when it increases and decreases, that indicates a possibility of a local maximum. And in fact, graphically, this does have a local maximum. We'll localize around c. And so if you wanted to, you could label this generically by writing c minus delta sub 1 up to c plus delta sub 1, where delta sub 1 is greater than 0. All right. Notice in that little local interval, there is a corresponding function value, and those corresponding function values are up there. However, there is the biggest y value that is locally bigger than everything else, and that is right there. And that is called a local max. F of c is a local max of the function. Okay, notice when we talk about maximums or minimums, they're always y values, so you have to indicate f of c. Look at the next one. Let's localize around the number d. If we localize around the number d, here, why don't I make this interval bigger? And we call this d minus delta sub 2, d plus delta sub 2. Now your I is this. And once again, there are corresponding function values or y values. But in this local neighborhood, there's one y value that is lower than everybody else. It's right there, right? You could have y values here, but there's one that is the lowest locally. So there it is. Another way you could see this is that the function was what? Decreasing and then increasing. So we know that f of d is a local minimum. Now, what is an absolute max? Well, according to the definition, these aren't too difficult to spot as long as you have a picture. Absolute max in the entire world here, or the entire interval from A to B, the function is on the entire interval from A to B. So you could think of the entire domain of the function here as the world or the universe that this function lives in. So when we talk about absolute, you must investigate the entire domain and you make all the comparisons there. Notice the highest point is right here compared to all the other y values, and that becomes the absolute max. So f of e is the absolute max for the function. Similarly, we look at the entire domain for absolute min, and notice it's f of a. That will get you the absolute min for the entire function. Well, let's look at a theorem and compare this picture with this theorem. The theorem goes something like this. If the function has a local max or a local min at c, and the derivative evaluated at c exists, remember exists means finite number. Well, then that derivative evaluated at c must be 0. Okay? Another way to visualize this is to remember that this is the slope of the tangent line evaluated at c. So remember, it's the slope of the tangent line to the function evaluated at c. So if you look back at the previous example, once again, if the function has a local max, and this one does, then and it has a derivative that exists, then that derivative evaluated at c must be 0. And notice that is just the slope of the tangent line. Same thing with the local min. Okay, if the function is differentiable and it has a local min and it's differentiable, then the derivative evaluated at d must indicate a slope of a tangent line of 0. All right. Now, the converse of this theorem is not true. Okay, the converse goes something like this. If the derivative evaluated at c is equal to 0 and f has a local max or local min, if f prime of c does equal 0, then f has a local max or local min at c, and the first derivative exists. This is actually false. So we could do a quick counterexample here. Look at x cubed, and you want to look at this locally around x equals 0. So the derivative here does exist. However, there is no local max or local min there at x equals 0 or at c equals 0. Okay, clearly there are some values that are less than 0 and there are some values more than 0. There is no local max or min there. Even though the converse is not true, it gives us enough motivation to study functions in such a way to look for minimums and maximums. And when we look for these minimums and maximums, we're really going to rely on a differentiable function, okay, which gives us the following definition. If f is a differentiable function, then any c in the domain of f such that f prime of c is equal to 0 is a type 1 critical number. Or when f prime of c does not exist, is also a type 2 critical number. We say c here is a critical number of f of x. These c values are critical because it gives us that possibility of whether or not a local max or local min exists, or whether or not an absolute max or absolute min exists. It just gives us the permission to go out and seek maxes and minimums of a function. Why don't we try this by looking at a function? Let's perform our basic rules of differentiation and look for both types of critical numbers. I'm going to go ahead and use function notation. And algebra says we need to find a common denominator. Once you have common denominator, we can go ahead and subtract the numerators. And we're going to need the first derivative in a very good form. Usually reduced factored form is probably or is going to be the best form you could have of a derivative. So reduced factored form, there it is. And now we're ready to analyze this first derivative. The way we're going to analyze this is by finding critical numbers. So type 1 critical numbers occur when the first derivative is equal to 0. So we're just going to set that equal to 0 and then solve for what? C squared. And then the denominator is 1 plus c squared. Multiply both sides by 1 plus c squared, and we now get 0 is equal to c squared. C equals positive or negative 0, which is silly because 0 is a number without parity. So it's okay to just say c equals 0. C equals 0 is a type 1 critical number of the function. Now, how do we get type 2 critical numbers? We look at the first derivative, and we need to make sure, or we need to analyze, when does this first derivative does not exist? Well, it does not exist when you try to divide by 0. So if you take the function and you set the denominator equal to 0, you end up solving this equation. In this case, there is no real solution. And we'll finish with, thus, there are no type 2 critical numbers. So a key here is that if the first derivative is a fraction, make sure it's in reduced factored form, and that way you could go on and seek type 1 critical numbers first, and then try to seek type 2 critical numbers second. Now, what's an answer to this problem? Well, everything. Make sure you indicate your first derivative function, as we're going to need that later on. We are going to need that for the first derivative test. Now, I just realized I forgot the letters again. This should be the letter C. Now everything is consistent. I'm going to circle an answer. An answer to this problem is actually, yeah, everything.